Okay, next we have sinusoidal wave on a string. So until now we discuss just a single pulse, like suppose this is a string. I consider the string to be connected to a support from one side. This is the support. Now if we give a small jerk to this string in the upward direction, then we produce a pulse in this way. This pulse has a maximum displacement, or we call it the amplitude, which is A. So we create this pulse with maximum displacement of the medium particle by giving a jerk to this string in the upward direction. Similarly, if I give a jerk in the downward direction, then the pulse will create like this. We give a jerk to the string in the downward direction. So a pulse with maximum displacement or negative displacement, this is now in the negative y direction. So here this is the maximum displacement A now. So a pulse with maximum negative displacement of the medium can be created by jerking the string in the downward direction. And similarly, a pulse with maximum positive displacement of the medium particle can be created by jerking the string in the upward direction. Now if we jerk the string both in upward and downward direction in a periodic manner, then we create a number of pulses in the string. We create a number of pulses. The pulse with maximum positive displacement can be created by jerking the string in the upward direction, and similarly a pulse with maximum negative displacement of the medium particle can be created by jerking the string in the downward direction. So the original direction of the original position of the string was this one. Now here we are giving a jerk. We jerking the string both in upward and downward direction in a periodic manner. So by this way we create a number of pulses, both with positive displacement and both with a negative displacement. So the creation of this number of pulses is called a train of wave. Train of wave. So if we jerk the string up and downward periodically, we can produce a number of pulses. Here we have a number of pulses which we create by jerking the string both in upward and downward direction with alternating positive and negative displacement of the medium particle. By this way we create a train of pulse. Normally call it train of wave or wave train. We call it train of wave or wave train. Now the string is said to be oscillating by an external source, like we have applied an external force here, and this string is said to be in oscillation by this external force F, both in upward and downward direction, and this force is periodic because in one interval we are jerking the string in the upward direction, in the next interval we are jerking the string in the downward direction, and then the next jerk is upward and then the next one is downward. So this is the external force we applied in the in simple harmonic motion way. So each point of the string, now suppose this is one of the point I consider on this string, one of the point on this string. Let's suppose this is the point on the string. Then this point also oscillate periodically both upward and downward direction. Thus every segment, so this is a point, so it means that every segment of the string can be treated as simple harmonic oscillator. So if I consider a small segment of this string, then this segment can be treated as simple harmonic oscillator. Why? Because this segment move up and move down periodically. Once a number of a wave train is passing through this string. So in one time it's look like this, in the other time it looks like this. So it's oscillate both in upward and downward direction. So this segment can be treated as a simple harmonic oscillator, and which is vibrating with the frequency, which is vibrating with a frequency which is equal to the frequency of the external source. Like the source which vibrate both upward and downward direction with a specific frequency, so that frequency can also be transferred to the string. So this pulse, this segment of the string is treated as a simple harmonic oscillator which oscillate with the frequency of the external source. And also we have to note that each segment of the string oscillate in y direction, because this is a wave. The wave moving in forward direction. Let's suppose this is x, this is y. The wave is moving in the forward direction, like in the x direction, while the particle of the medium of the string, or the segment of the string, is moving up and downward. So the segment move up or down. It's moving along y direction. So the wave moving in the x direction with velocity v, while the segment is moving in the y direction with velocity, which I call it vy. So we have to recognize these velocities. So this velocity is the velocity of the wave, because once we create a wave, the wave is moving in the forward direction along the string. So this is the velocity of the string, and we know that the particle of the string, or the segment of the string, is moving up or down, because if this is the segment, it's moving up, then it goes down, and then it goes down again. So it's moving up and down, so its velocity is represented by vy. So whenever there is a vy, it means that this is the velocity of the particle of the medium. Whenever we have only v, then it represents the velocity of the wave. Okay, the wave in a string behave like a sinusoidal wave, because this behave like a sinusoidal wave. Its shape is like a sinusoidal wave. So the wave function for the wave producing in a string can be represented by this y, which is equal to a sine kx minus omega t. This is a sinusoidal wave. And we know that a wave is producing a wave creating, like when we create a wave in a string, it's look like its behavior or its shape looks like a sinusoidal wave. It follows this equation, but it's obey this equation. So this is the wave function for the wave producing in the string. Now any point on the string can move only vertically upward or downward. So its x coordinate will be constant, because if a particle of the medium is moving up or down, then along this line x is constant. So we keep x constant throughout the derivation for the velocity of the particle. Now the transverse speed, or the speed of the particle, we represented by vy, which is equal to dy over dt by keeping x is equal to constant. Now y is a function of both position x and time, because here we have the position x and time. and x is constant, so we represent this vertical component of velocity or the transverse velocity or the velocity of the medium of the particle by partial derivative, partial y over partial t. Because for the derivation of the velocity of the particle, we keep x is equal to constant, and this y is a function of both position and time. So this position x is constant, so it means that we will not use the general derivative dy by dt, so we use a partial derivative. So this derivative means partial y over partial t if y is a function of x over t implies that x is constant. Now we have y given there, so we have vy which is equal to partial by partial t a times sine kx minus omega t. Now a is constant, so I can keep it outside of the integral derivative, sorry. So we have partial by partial t of sine kx minus omega t. If we take a derivative of sine with respect to t, we get minus omega a cos kx minus omega t. This is the transverse velocity or the velocity of the particle of the medium. It's represent velocity of the particle of the medium. While we already derived the velocity of the wave, which is v, which is equal to force per unit. This mu, and mu represent the linear charge density. Now similarly we can calculate the acceleration, and acceleration is we have the acceleration which is equal to dy by dt. Y means acceleration of the particle of the medium. So for that we keep x is equal to constant, because if a particle move up and down, then at this point x is always constant. So if we put it, if we solve this equation, sorry, dy, it's dvy, rate of change of velocity, dvy over dt, by keeping x is equal to constant. So if x is equal to constant, then this total derivative is replaced by ay partial derivative. Partial derivative. So taking the partial derivative of this equation, so here minus omega a is constant, so I can keep it outside of the integral. So we left with partial by partial t of cos kx minus omega t. So from cos I get minus sign, so 1 minus there, 1 minus there, so it's a plus. And then again derivative of this we get minus omega, so overall there is a minus sign here, and we have omega square a sine kx minus omega t. This is the transverse acceleration. It's represent, this is transverse acceleration. Or it's represent the acceleration of the particle of the medium. Let's represent the acceleration of the medium particle. Now acceleration is given by this equation. Let's suppose this is 1, and velocity is given by equation 1, and acceleration is given by this equation 2. Now the maximum value of velocity, the maximum value of velocity is, velocity will be maximum velocity will be maximum if the value of this cosine of this kx minus omega t is maximum, and the maximum value of cos is 1. So the velocity will be maximum if cos kx minus omega t is equal to 1. So this implies that the maximum velocity Vym is minus omega a. And similarly, if you look at this equation, the acceleration will be maximum if the value of this sine kx minus omega t is maximum. If this value is maximum and the maximum value of sine kx minus omega t is 1, will be maximum if sine kx minus omega t is 1. So the maximum value of acceleration will be minus omega square. These are the acceleration and velocity. This equation 3 and equation 4 represent the maximum velocity and maximum acceleration. Now if a particle is moving, like this is the particle of the medium or the string, let's suppose this is a string, this is one of the particle. I suppose this is one of the particle of this string. So this particle either move up or it's move down. So once this particle reaches to its maximum displacement, then its velocity will be equal to 0, because once the particle reaches to its maximum displacement, then after that it cannot move beyond this point, so it will move downward again. So at this point the velocity will become 0. So at this point acceleration will be maximum. So here at this point the velocity is maximum while acceleration is 0, and again at this point velocity will be 0 and acceleration will be maximum. This is all about sinusoidal wave on a string. Thank you.